Hi guys. Thank you for choosing this video. First of all, I would like to ask some questions. Have you ever heard about PFAS? Do you know what it is and the impact of it? If you are not familiar with, no worry, this video is going to answer these questions and also introduce how to treat the PFAS-composed municipal solid waste and also the leachate generated from it in landfill by using photocatalysis method. So let's begin the journey. In this video, there will be 4 parts. Firstly, what is PFAS and the problem of it? Secondly, source of PFAS. Thirdly, different disposal and managing treatment for PFAS, and finally how to manage the waste of PFAS by using photocatalysis method. What is PFAS and the problem of it? PFAS is the abbreviation of perfluoroalkyl and polyfluoroalkyl substances. They are a group of man-made chemicals that includes PFOA, PFOS and Gen X chemicals. Since the 1940s, PFAS have been manufactured and used in a variety of industries around the globe, including in the United States. PFOA and PFOS have been the most extensively produced and studied of these chemicals. Both are very persistent in the environment and in the human body. Exposure to certain PFAS can lead to adverse human health effects. The problems with PFAS is: firstly, short for PFAS, chemicals used in products such as non-stick cookware, food packaging, water-resistant clothing, and stain-resistant carpeting. Secondly, they also called forever chemicals, which means they can take up to 1,000 years to break down in nature. You might not have realized how closely PFAS is related to us after listening to the previous theoretical introduction. Actually, PFAS is all around us in our daily lives. It's in waterproof clothes, non-stick pans, food bags, cosmetics, and the electronic products we use frequently. PFAS is used as a plating layer in these things and has quietly made its way into our lives. So where do they really come from? However, there are mainly 4 main sources of PFAS. One of the main sources is the PFAS processing factory. Specifically, during the production process of PFAS-containing products, waste containing PFAS is generated. If the environmental protection facilities are poor or not properly operated, PFAS will be directly discharged. Also, during the storage, transportation, and use of PFAS-containing products, if the packaging is damaged or leaks, the PFAS-containing products will be released. The second source is the wastewater treatment plant. PFAS is used in industrial production, or PFAS-containing wastewater enters through sewers. Sewage is produced from the use of PFAS-containing products. During sewage treatment, PFAS precursors may be transformed into PFAS. The third source is firefighting foam AFFF, which contains PFAS. The large amount of PFAS used during firefighting training and extinguishing operations will cause PFAS to enter the environment. Improper storage or disposal of PFAS will lead to pollution leakage. The fourth source is landfill leachate. The decomposition of household waste containing PFAS in landfills and the landfilling of industrial waste containing PFAS will cause PFAS to enter the leachate and pollute the soil and groundwater. So, while PFAS brings convenience to our lives, it also brings environmental and health crises that cannot be ignored. Because it is persistent and difficult to be biodegraded, once it enters the environment, it will accumulate for a long time. Research has found that PFAS not only pollutes water and soil, breaking the ecological environment, but also enters the human body through the food chain, jeopardizing human health. Certain PFAS substances are closely related to cancer and reproductive diseases. Different disposal and managing treatment for PFAS. One common method is activated carbon adsorption. Activated carbon is an adsorbent with a highly porous structure that can effectively adsorb PFAS. The adsorption effect of different types of activated carbon on PFAS varies. Both granular activated carbon and powdered activated carbon have a certain removal ability. The advantages are relatively low cost and easy availability, but it may reach adsorption saturation and require regular replacement, and the adsorption effect of some long-chain PFAS may not be as good as that of short-chain PFAS. Advanced oxidation processes AOPs are also employed to address PFAS contamination. AOPs use strong oxidants, such as ozone or hydroxyl radicals, to chemically break down PFAS. It can efficiently remove PFOS, avoid secondary pollution, but the technical requirements are high, requiring professional equipment and operators, and the cost is also high. Reverse osmosis filtration systems are generally considered one of the most thorough and widely used water filters on the market today. In the process of reverse osmosis, water is transported at high pressure through a semi-permeable membrane, which has tiny pores of about 0.0001 microns, and PFOS is usually much larger than these membrane pores, with a filtration rate of up to 90%. During the reverse osmosis process, the persistent PFOS, and hundreds of other trace pollutants in the water will be treated. Its removal effect is very good, and he can simultaneously remove multiple other pollutants. But it requires high pressure, consumes a lot of energy, and generates a certain amount of wastewater, which needs to be properly treated. Resin adsorption is another effective strategy. There are two types of ion exchange resins, anionic resins and cationic resins. Positively charged anionic resins can effectively remove negatively charged impurities, and PFAS usually carries a negative charge, making anionic resins the best choice for removing PFAS. This solution often has higher capacity than activated carbon water treatment, but its upfront cost is higher, so developing suitable resin materials is crucial. In summary, the management of PFOA in landfill leachate involves a variety of innovative treatment technologies. Continuous advancements in these methods will enhance environmental protection efforts and help mitigate the impacts of this persistent pollutant on ecosystems and human health. How to manage the waste of PFAS by using photocatalysis method. This figure shows the transformation of PFAS-composed municipal solid waste to leachate with PFOA, which is the subset of PFCA showed in this figure. So you can see PFCA as PFOA here, and after disposing the MSWs into the landfill, leachate like FTCA and PFCA will be produced due to the degradation of PFAS-composed municipal solid waste undergoing by the microorganisms digested anaerobically. And here shows the mechanism of photocatalysis in degrading PFOA. And according to the equation showed above, firstly a catalyst will absorb energy which can be stated as HV, and if the energy is equal to or larger than the band gap of the catalyze, then an electron and hydrogen ion pair will be formed. After that, this pair will separate into one free electron and one free electron hole. Normally speaking, you can see that from the equation 3 to 6, the electron hole alone can already degrade PFAS directly. But if we look at the equation 2, the free electron hole will react with H2O in the solution and produce hydroxyl radicals. The hydroxyl radicals can help degrade organic compounds with hydrogen atom with abstraction to form water. But in the case of PFOA, as fluorine atoms replaced all hydrogen atoms in the carbon chain, and therefore the carbon chain of PFOA is inert to the hydroxyl radicals. Therefore, it can be concluded that transformation with less free electron hole transformed to hydroxyl radicals will be preferred for photocatalytic process of PFOA degradation. And here is the review of the effectiveness of the 5 different catalysts: gallium oxide, titanium dioxide, cerium oxide, indium oxide, and cadmium sulfide. The degradation rate constant for different catalysts can be calculated by using pseudo-first-order model to calculate the degradation rate constant K. And the result is that gallium oxide has the highest degradation rate, followed by titanium dioxide, cerium oxide for the third, indium oxide for the fourth, and cadmium sulfide has the least degradation rate among the 5 catalysts. And therefore, catalyst with higher degradation rate is preferred for the photocatalysis process of PFOA. After watching this video, hope you can get more familiar with PFAS and the treatment of PFOA, the leachate which generated from PFAS municipal solid waste in landfill, by using photocatalysis method. Thank you for watching and hope you enjoy it.